In the previous lessons, we focused on how fast a system responds and how much it oscillates. But there is another critical question. Does the output actually reach the desired value? The difference between the desired and actual output in steady state is called the steady state error. Today we learn how to predict this error without simulating the system.
Consider a unity feedback system. The input is R of S, the output is Y of S, and the forward path transfer function is G of S. The error signal is E of S equals R of S minus Y of S. Using the closed-loop relationship, we can write E of S equals R of S divided by 1 plus G of S. The steady-state error is found using the final value theorem. E steady state equals the limit as S approaches 0 of S times E of S. The system type is the number of pure integrators in the open loop transfer function G of S. A type 0 system has no integrators. A type 1 system has one integrator, meaning one S in the denominator. A type 2 system has two integrators. The system type determines which inputs the system can track with zero error. Higher type means the system can track more complex inputs perfectly. For a unit step input, R of S equals 1 over S. The steady-state error becomes 1 divided by 1 plus Kp, where Kp is the position error constant. Kp equals the limit as S approaches 0 of G of S. For a type 0 system, Kp is finite, so there is a non-zero steady-state error. For type 1 or higher, Kp is infinite and the error is 0. Watch the step response. Type 0 settles to a value less than 1. For a unit ramp input, R of S equals 1 over S squared. The steady-state error becomes 1 over Kv, where Kv is the velocity error constant. Kv equals the limit as S approaches 0 of S times G of S. A type 0 system has Kv equals 0, so the ramp error is infinite. The output falls further and further behind the ramp. A type 1 system has finite Kv, giving a constant position offset. A type 2 system tracks the ramp perfectly with zero error. For a unit parabola input, R of S equals 1 over S cubed. The steady-state error becomes 1 over Ka, where Ka is the acceleration error constant. Ka equals the limit as S approaches 0 of S squared times G of S. Only a type 2 or higher system can track a parabola with finite error. Type 0 and type 1 systems both produce infinite error for parabolic inputs. Let us organize everything into one table. For a step input, type 0 gives error 1 over 1 plus Kp. Type 1 and higher give 0 error. For a ramp input, type 0 gives infinite error. Type 1 gives 1 over Kv. Type 2 and higher give 0. For a parabola input, type 0 and 1 give infinite error. Type 2 gives 1 over Ka. Type 3 and higher give 0. This table is the key result. Each row is an input type. Each column is a system type. Let us work an example. Given G of S equals 10 times the quantity S plus 2 divided by S times the quantity S plus 5. First, identify the system type. There is one S in the denominator, so this is a type 1 system. Kp, the limit as S goes to 0 of G of S. The S cancels, giving 10 times 2 over 5, which is 4. Wait, for type 1, Kp is actually infinite because of the integrator. Kv, the limit as S goes to 0 of S times G of S equals 10 times 2 over 5, which is 4. So for a step input, the error is 0.
For a ramp input, the error is 1/4, which is 0.25.
To summarize, steady-state error depends on two things: the input type and the system type. The position constant Kp, velocity constant Kv, and acceleration constant Ka are found by taking limits of g of s. The error table tells us everything. Higher system type means lower error for each input. In the next lesson, we study the root locus method, which shows how closed-loop poles move as we change the controller gain.